ಕಾಣಿಸ್ತಾ ಇದೆ ಬಟ್ ಆಡಿಯೋ ನಂದೇ ಏನೋ ಸಿಸ್ಟಮ್ ಸರಿ ಇಲ್ಲ ಅನ್ಸುತ್ತೆ.
Hello. Okay. Good afternoon to whoever have participating in this live, what I should say is doubt clearing session. So welcome to the session, and then thanks for joining and then taking this course in your this thing. I don't know whether it is curriculum or hobby to learn or whatever may be the thing. So I hope you're enjoying the course. So if there are any questions, I'll just take it up after 2 to 3 minutes of briefing you. So just to tell you what is this real-time signal processing. As you know that we call this as a clocks basically if I have it. So I can draw the clock. So we say this is our data which is coming as input. So what we have to do is what is real time, because in each clock we may be getting some data. So we are supposed to process it within this duration. I think in the first class itself, I have clarified that usually we give computation time, we take it as somewhere around 40% to 50%. And what we call it as overheads, basically taking the input data and then other thing which constitutes to either it can be 50 to 60%. So we know that we are going to have only this amount of data, which in the time we have to do it all the computation, whatever it may be complex or simple or whatever may be the thing, what you have to do it. So coming to the thing, what we have covered is a little bit of architecture. what may be the clock speed the DSP processor can take it. And then what we went on to learn about some of the how it can be made faster. One is pipelining and then parallel processing to increase the computation time. The other way we looked at it is how we can reduce the uh, power consumption by basically if you are designing any FPGA or what by using FPGA, if you are designing any of your circuits, so how you can reduce your computation by doing um, uh, parallel processing and then pipeline. So both, so we worked out some of the problems in that also, how we can reduce the voltage levels. So if it is the 5 volts, so by selecting proper beta based on your pipelining and parallelism, we can reduce the thing to beta squared basically. That will be the operating voltage of your circuits. So that we have considered it. Later on, we started using filters. Basically, we did the thing, FIR filters and then IR filters. As we know that the little difference between, I'll little bit highlight, I think most of it is covered in the course. So we know that here it is going to be, we call it as a feed forward basically circuits, what we'll be designing it, and how we can reduce by looking at some of the, if we reverse the circuit, even the your circuit also is going to matter. So if I have my feed forward circuit, sorry, I'm putting the thing in FIR. If you are looking at y of n will be in FIR will be, I can call it as B naught into x of n, B1 into x of n minus 1. So if I take the second order, so this will be your circuit. Based how you can look at your algorithm, and then by just input and output, if it is reversed, okay. So how the delay elements can be ordered, and then I can from the architecture point of view, which is going to consume one multiplier and then two adders, we can bring it down to one multiplier and then adder. So that way our hardware is also going to be reduced, and then our output is not going to change in the thing. So whereas in the case FIR, as we say, all of them are feed forward, and then the order of the filter in this case is going to be more. So compared to IR filter, this is a feedback. We have feed backward also, forward and then backward, both in the case of IR filters. So that way the order of the filter comes down very drastically compared to FIR filter for the same cutoff frequency what you are looking at. So this is my this thing passband frequency, and this is my stop band frequency. So how much I can come down with respect to order of the filter. So order of the filter, in case if you have done comparison, if you have used the MATLAB, so you'll be seeing that your order of the filter drastically comes down in IR filter. So that is one of the advantage. And then coming to the disadvantages, as we know that we have what we call it as second order sections basically in IAR filter. This is your, and then I can do the cascading of it. Why it has to be cascaded also, we have looked into the thing. This is, so this is B naught. This is B1, and then no. Make it here. So this is your B0, B1, and then B2. So we can either go for this is my input, and output, I'll call it only, I have taken a second order section. This is my A1, and A2. Somebody has asked why A naught is not considered. I think for that I have answered, because y of n is the current this thing output what we'll be calculating it. So hence what happens is only our this thing will be y of n will be is equal to b naught x of n minus 1. If I take the same thing, b1 x of b naught into x of n, b1 into x of n minus 1. These are the delays basically. As you can see, the thing z minus 1. So plus b2 into x of n minus 2 minus what we'll take it because it is going in the other direction. We can take a1 into y of n minus 1 minus a2 into y of n minus 2. So if the coefficients are negative, then this becomes this thing plus basically when you take a1, a2 coefficients. So hence this is the y of n is the thing. So which is scaled with a naught. Usually we assume that this is 1. Hence we don't have that coefficient a naught in this case. And one more, the thing is, we said that it is a direct form or indirect form or a cascade section, or it can be parallel also. I can have parallel or the cascade section. The result is going to be same. Only the disadvantage in parallel section is because we did not take it, because in the DSP processor, when we assume that we had considered the number system. So that one, what it comes into here basically, because addition can have a overflow. Whereas the multiplication is not going to cause me any overflow because we are considering fixed point implementation. That is the reason why even IR filter, we go with the cascade section. And why we need the cascade section also, because if we consider the complete this thing direct form implementation, any one coefficient is little bit modified, entire section it gets altered. So everything has to be looked into the thing. Whereas in this second order section, only the whatever perturbation is going to happen, it is restricted in this section. So this, I think I've covered it more in the thing. Just to give you a hint, I'm putting it here. So that is how we get whatever the order of the filter, as you can see in this. Only the disadvantage is here is we have this, we call it as W of n. If you take the thing, there are two additions what we have to do. So there is going to be one adder and then one more adder what we'll be having it. Whereas in the second order section, if it is a direct implementation, we'll have only one adder. So whatever the negativity coming from here and then positive thing, they make it nullified. But whereas in this case, what happens is if both are negative, so we may go for overflow and then the addition also if they're positive. And if we are adding it, they may overflow. So we have to take care of the overflow conditions in this case. But we have reduced the storage and then storage elements basically in the case, which is fully detailedly explained in the thing. So this is regarding the filters what we discussed it, and then so the next what we have taken was the DFT part of it, DFT and FFT. So DFT is an algorithm, whereas FFT is just a implementation of DFT in the faster way. So the advantages and disadvantages, what we have order of the computation, what we have looked at it. So if I take the second order or 1D DFT, if I take the thing, so we need order of n squared multiplication and then order of n into n minus 1 additions. Whereas in the case of FFT, if we implement the same thing, it will be n log n, log 2 n what we'll be having the computation. So if it is for 2D, so we'll be seeing that it will be order of n squared into log 2n, and then you can implement them. So one of the disadvantage or whatever we look at it is, we know that input in case of FFT is going to be a bit reversed order. So we have seen that how the bit reversal is going to happen in the architecture, which is inbuilt. So if we consider 0 is my input, so n is, if I take it as n is equal to 8, then what we do is n by 2 is equal to 4. So which is nothing but in binary 1 0 0. So we do the addition, what we said it is going to happen in your DSP processor, which is inbuilt. Usually we add from right to left. Whereas in the bit reversal addressal generation, we add from left to right. So if you take it, this will be first address 0 0, your 0 value is going to be stored. And then this is your 4 basically. And then next is if you add 1 0 0, so you'll be seeing that 1 plus 1 0, so you'll be carrying it here 0. So next value will be your second. As you can see the butterfly structure, if you are looking from the thing. So initially we have the butterfly, first stage is going to be considered. So this is in continuous form what you have it. If you have stored in the continuous form, or it will be x of 0, x of 4, x of 2, and then x of 6. Next, if you add the thing 1 0 0, it is going to be 1 1 0. So here it is going to be, when you add this one with respect to this, you'll be getting 0 0 1. So this will be your x of 1 and x of 5. As you can see, you can add it x of 3 and then x of 7. So input is going to be in the bit reversed order, what you have to access from the memory. So these are the storage elements, what you are going to, how we are going to take it from, because as we know in the memory location, x0 to x7 continuously it is stored, but we want to access whatever value here. We need not have to spend much time on it. So hence this automatically in the hardware bit reversal access is going to be happening, and I'll be taking the data from this way. So then we'll be combining, this is the first stage, what we looked at it. And then if we consider here, it is only addition or subtraction is going to happen. So some of the thing from n log to n, we can bring it down further with number of stages, okay? So you will be combining the second thing here. So the same way here, you'll be doing it. In the final stage, you'll be combining all the butterflies, okay? So from this stage to this stage and from here to here. So you will be seeing that what is the number of butterflies required in each stage, you will be looking at it. So it will be n by 2 in this case. And here also it will be n by 2, so which remains constant throughout your thing. And then as you can see, it is log 2n what we said computation for 8-bit. So you will be seeing that it is going to be number of stages required is 3 stages what we need. Fine. That way it becomes faster in the case of our computation. So this is what we covered. And then do you have any questions till now? Or any of the thing covered? Okay. Is it in FIR filter you want to have it, or in IAR filter?
FIR, ma'am, FIR.
FIR. FIR, you will be usually we use is windowing technique. Okay. So have you used the MATLAB?
Yes, I'm just going through with your course. So I was very grateful to find your course on NPTEL. So I'm working professional. I am working in Fujitsu research.
Okay. Okay.
So here we are doing those things. I mean, I got a lot of help from your course. So little
Okay.
bit intuitive understanding I'm just going through.
Okay. So what you sorry, I don't have the MATLAB to show you immediately. So if you go to the filter design, okay, use the
Yes.
toolbox in the thing. So there you can select which filter you want to have it, FIR filter or IR filter. If you select the FIR filter, it will ask you default, it goes to Kaiser window. So in the
Yes, yes.
Kaiser window, we have alpha and beta, which you can select it. Whereas in the other windows, so it is fixed.
Okay. Means, ma'am, I want to introduce understanding like suppose we want to give some pass band, right? Like 950 to 950,
Yes.
960 band, uh,
Okay.
960. So how, I mean, this B
This
not
is your
given?
950
Yes,
and this is 960, correct?
yes,
What you want, this is your pass band, this is stop band. And then
yes.
I need, you have to give the thing. This is, we call it as this thing. What is it? Is one, okay. This
Mhm.
is in dB basically, up the thing got down. Fine. So
Yes.
how much dB I want to come down to stop band? Okay. So it depends on your cutoff frequency. So because this is very narrow band, what is only 10 hertz what you have the difference. Okay.
Means
So what is
I'm
your
talking about
sampling frequency?
megahertz, ma'am. Megahertz, like 950, like in our radio in
That's okay. What
5G.
is your sampling frequency? Tell me the thing.
Sampling frequency, suppose 30 megahertz something, some 30 point something megahertz. Generally, we are choosing for 20
30 megahertz, but this cannot be 950 megahertz and 960 megahertz, correct?
this will be
Usually,
15.36 something in this case.
uh, okay. See, we have given that basically to reconstruct your signal, okay? This
Mhm.
should be twice maximum of frequency that is present in your input. That is what the sampling theorem says. But in implementation, usually we look at it as approximated to 4 to 5 times of your maximum frequency. Because if you take just 2 FM, if it is a sine wave, we know that all zeros what we'll be getting it when we sample it, okay?
Okay.
So that is the reason why usually we sample this one 4 to 5 times more than the maximum frequency present in your input.
Yes. Yes.
It has to be sampled that way, fine?
Okay. Yeah.
So if you are having 30 megahertz as the thing, okay, I'll come down, I'll erase this. This is what you said, 15 megahertz, and then it doesn't matter because it get cancelled. 15 and what is it? Something, what will be your
Generally, ma'am, in like we need to do baseband processing, then after we need to up convert. So in baseband, in the case of baseband, I'm talking about like if 20 megahertz we have bandwidth, then in that case we are taking like a 30 point something megahertz as a sampling frequency because we are going from minus f to plus f. So in that case, it will meet the 2fs criteria, means 2fm criteria in
oh,
baseband processing. Then we need to up convert like 950 to 970 megahertz.
okay, then you will be using a interpolation technique to do the thing, that is adaptive this things um sorry, um upsampling and then downsampling, what you will be doing it. I think I did not cover in this course how to do the thing. So how to upsample the thing and downsample, as if I think in one of the ADC, I have told that it is sampled at a high rate because we use the sigma delta ADCs and then we sample it at a high rate. And then somebody asked what happens to the noise. Okay. What happens is noise is going to be distributed over the complete frequency range and then we do the cutoff. Okay, so that way noise is spread over so that we are reducing it. Earlier it used to be successive approximation and other things what it was used, and number of bits used to be 8-bit or 10-bit maximum and then 12-bit ADCs. Now we can increase little bit of number of bits also. You'll be seeing signal to noise ratio also what is coming into the picture. Okay, so that way we upsample it and then do the downsampling later on. So that part I did not cover in this course. So hence what you can do is, once again, go back to the thing. So whatever you have the thing, so if I take it as something, I'll call it as your 20 megahertz is your this thing difference between the thing, then I'll be having it as 35 here. Okay, so the bandwidth is this. So this will be your input. I think you may not be able to work in megahertz in this thing, MATLAB. So you can properly scale it down and then look at the thing. So your passband frequency is this and the stop band frequency is this, what you can give it. And then if you want the order to be, because it depends on if you give this way, if there is a narrow band, order of the filter may go very high. So as it is discussed in the architecture, so the overflow, what we can, most of the 16-bit this thing DSP process, they provide what is it? Excess addition. That is what we can do is only up to go up to 40-bit. So they'll call it as 8 bits if it is a 32-bit. So we have 8 guard bits, what we call it in the architecture. So they can take overflow up to this thing. I can do 40-bit addition, not more than that. Although I'll be using 2 registers. Registers are 32-bit each, but we'll be combining 2 registers, only 8-bit of one of the register and 32-bit from the other register, what pair, what we call it. We use it to do 40-bit addition. More than that, it is not possible. It has to be scaled down to that. And then it depends on, as I put it, it is a fixed point what we'll be using it. So if it is a 16-bit processor, so what we can go is minus 32767 is in integer format to plus 68 to 32767. This is a maximum values what it can take it in integer format. So usually we represent it in this thing fixed point. So if it is integer, we assume that it is 1.15 format, 15 bits. Sorry, if it is 1.15 format, this has sign bit is this one. Rest of it, I'm allocating it as a fraction. So it depends on the thing, how you do it. If it is 2.14 format, so totally 16 bits only. Here, what happens is one sign bit, the other one bit it can take. We know that it is 2 is the maximum value, 2 point something what you can take it. So that we have discussed that in the fixed point format. So what I say is as addition and other things is the thing. So maximum 8-bit guard bits, what we have the thing, which is equivalent to 2 power 8 is 256. So you can maximum your order of the filter, what I'm talking about, what you can design is 256, but be careful if there is a overflow, even FIR filter is going to go for a toss. So it depends on whatever B0 coefficients to B1 coefficients, and then input whatever range you have taken the thing. So that is the reason why most of the time we do it divided by 2, not more than if it is correctly designed, we can go up to 256 or even 300, it has taken the thing. But you have to design a stable filter. Even FIR may become unstable in that case. So usually we try to do 128th order or something like that. So if you allow it to go only with your band, this thing, it may cross the order of the filter. So you have to do what I'll put it as take care of these issues before if you are putting it on the crosser. If you are designing your own FPGA, then number of bits what you are going to design is going to be entirely under your control. So if it is completely built-in processor, if you are using it, as you know, if it is a floating point, I can go from whatever bandwidth basically from low value to higher value. Fine. So any other questions? So these are the things what you have to take it into consideration.
Thank you. Thank you.
Any other queries?
So generally, ma'am, I have one more doubt.
Ah.
So like in wireless communication, generally we are following the fixed point computation or floating point computation.
Yes.
Wireless application, like at radio side or layer one side.
Okay. Fixed or floating point. A floating point. The problem is if you're. I'm telling if you're using your own designing it basically. Floating point addition will be taking in. If you look at DSP process 67, 647, whatever we have given the thing. Okay, processor. So it can take both fixed point as well as floating point. So floating point addition may go up to 10 clock cycles because you have to adjust both the exponent and then add it. Okay. So in the floating point additions. So if there is a faster thing way of looking at it, there are this thing, what is it? Algorithms which have built in to do faster additions and other things. So that is how we have seen that our barrel shifter, that is how you can shift the thing, that is division or multiplication, you can do it faster, or drawn multiplier what we have taken, how you can do there also pipelining and then parallelism. And in the last stage, as you can see, it can be carry ripple adder or any other adder what you can use it to do basically fast additions. So these are the ones which will be restriction your computation basically.
Okay. Okay.
And
Ma'am.
even what you have to do, overflow, one has to consider.
Okay.
Okay. Okay, somebody has commented that interested in this topic. Fine. So regarding the ISRO, okay. So this I won't be able to comment. So you have to go to the ISRO site and then you have to look into the thing, what they need it basically. So depending on it, what you have to prepare. So I'm not a competent authority to tell the thing. Regarding the course, I can put the comment on it. So any other doubts you have it? Or any other briefing you need or other topics?
Ma'am, compression technique you also cover in, that is also kind of DSP, like some like in our
Yes.
video we are using BFP, block floating point compression technique. So we are 16-bit to 9-bit we are doing. So for IQ data, so those things also you will cover in going forward in our course somewhere.
Compression and then this thing, compression only in the from the point of view of image processing, what we have looked at it, what can be the compression you can get it. Okay. So a little bit of applications what I've taken in the later part of it. So you'll be seeing in the image processing, compression is looked at. So whether it is a lossy compression or lossless compression, what we have looked into the thing, how the coefficient can be quantized, and then quantization technique we'll be looking at it, and then see that using DCT or only DCT part what I have covered it because of the time limitation and other things. So you can look at any other algorithm which gives you compression and then whether it is a lossy or lossless, what you can have a look at. Okay. So otherwise, from the signal processing point of view, it has to be upsampling and downsampling. Okay. So that part I did not have the time and then I had not covered in this course.
Okay. Okay.
Okay. And then multi-rate sampling, basically we do the thing for, that is one of the criteria for all these, this thing. So which I have not covered in the thing. There is a multi-rate signal processing, separate course is there. So one can, I think, have a look at it. I think.
Okay. Okay. I will search.
Course in NPTEL only for that, or
I'm not sure of the thing. We have to look at it, whether it has been covered. Digital signal processing, whether multi-rate also they cover or not, one has to look at it. Okay. Yeah. Any other queries from others?
Ma'am, is there any good, so like these fixed point, fractional point, number systems and all, right? Mostly, I could only find like the best reference material was the lecture slides themselves. But in case there is any textbook or anything where we can refer, which can kind of
They
recycle
will,
memory of that.
I think all the books, we have one book is uploaded, so you can look at this thing, their fixed point and floating point, little bit of it they'll cover. For this thing, most of the thing you may have to, because I have looked in different books, okay, multiple books, and then I collated and then
Right,
I
right.
have done the thing, because how it has to be done, because it is a bit level. Nobody gives the bit level addition or multiplication in the case. So because when you are implementing in FPGA, you have to go up to that level and then you should know about it, how it is going to happen. There also nowadays in FPGAs, you have the DSP blocks. You need not have to worry about it. So 16 by 16, they provide a 17 bytes, bit by 17-bit multiplier directly in the DSP blocks. You can directly use them and then give it, and then now you'll be getting it. But if you want more than 32, 24-bit or 32-bit, which we have needed in our application, so we have to build ourselves. In that time, it just comes in handy. And then if you're going for VLSI, basically, if you're designing your own FFT or scaling and other things, what you have to look into the thing before you come out with the circuit. So it is basically, I'll put it as a design course also, what I've looked at.
Okay, ma'am.
Yeah, any other questions?
Is there some section for this uploads and stuff on the NPTEL site itself, or?
In the under the course, this one there is a course material or course. This one there is there one section is there at the end. So you may check there, or otherwise I'll send a link tomorrow on discussion forum.
Yeah, I only see lecture material as in slides and stuff. I
Yeah.
don't see any textbooks, but yeah.
Check and we'll get back to you on that.
Yeah,
Or
you.
real-time digital signal processing by Q, you can take it, or this thing, even Chasiang is there. One more, Ifiker is also there, but there the number system, there is chapter 13, I think. I've forgotten the year of the book. After that, it was removed, okay. Even I could not get online, so I had to Xerox from, sorry, we had to scan the book 13th chapter in Ifiker. He gives the number system there, how to do scaling and other things also. That completely covers that part.
okay, ma'am, because like
The edition I've forgotten. I think it is 6th edition or something like that, Ifiker book. Okay.
I did go through Go, but there was like maybe just 2 paragraphs on it, and it was
Correct. Not much of them, but go to Ifiker. Chapter 13 covers it. If
sure.
there is any issue, then I'll ask them to, because we have scanned the hard copy of the book, that chapter alone, okay. So we
Okay,
can, I can ask them to upload it.
sure,
But there they covered cascade and then parallel everything, so you can have a look at it anyway.
sure. Thanks.
Yeah. Any others have any other question? Only I'm seeing only Sanjay Anand is maximally asking, and Deepak Singh also, I heard that he had asked few questions. Akansha, you have any queries? Okay, if there are no more questions, can we end the session? You can unmute and then tell me if you have any other, if you don't have any other questions. So we'll try to end the session.
As of now, I have no questions, so I will once go
Yeah,
through.
you can put it in the forum. Definitely, I'll try to answer. Okay,
Okay.
for the questions. Okay, thank you very much for joining.
Thank
So
you.
hope you will be get benefited out of this course.
Yeah, definitely. I am getting benefited a lot.
Okay, thank you.
Okay.
Okay.
Ma'am, one request.
Yeah. Yeah.
whatever you are taking in lab session, that code, if you put into the
Yeah, it is already been shared code actually.
I have checked, but many code I
Yeah.
didn't found.
Oh, okay. So I
Means
think
many
I'll ask
one-
them to put the link, okay? If there
Yes.
is any issue with the thing, I can take a lab session also if time permits. Let me see the thing, but I need little time because I have to set it up and then take it up the lab session. That's
Okay.
not a issue. If it is what is it, simulator, it can be done. Hardware means I have to connect the board and everything, and then I have to do the display for you.
Yeah, ma'am.
That's not
One hardware session will help us a lot.
okay. So we'll try somewhere. Don't push up to October. September, somewhere around September mid, I'll ask them to arrange one thing so that I'll also keep everything ready so that I can demo the thing. Few of
Okay.
it, some of them may be simulator, what I can show you the thing so that whatever you implement in the simulator, same thing can be done in hardware using the hardware, except there will be giving real-time input signal and then we'll be processing it and then output will be going through the board, okay? So except that difference, simulator and then your emulator, I think somewhere I've covered that what is simulator and emulator also. So we can look at the thing real time. You will be getting feed of it. Except some memory issues and other things may come up in your board basically. Although you may be selecting. Fine. Sometime I'll ask them to arrange in September one live session so that hardware can be taken it up.
Okay, ma'am. Thank you. Thank you.
Demos, whatever this thing I have asked the lab session, so that will be done. Okay.
Okay.
Okay. Thank
Okay,
you.
ma'am. Thank you very much. Thank you very much.
All the best.
Thanks.
Thank you.